closest star to Earth is not close. That is the first thing Proxima Centauri teaches us. Not that the universe is full of distant things. We already know that in a loose, harmless way. It teaches something sharper. It teaches that the nearest star beyond the Sun is still so far away that light itself needs more than 4 years to come home from it, and a spacecraft moving at the speed of Voyager would not arrive in a human lifetime, or in 100 human lifetimes, but after a stretch of time long enough for languages, borders, cities, and entire civilizations to change beyond recognition. Proxima Centauri is our neighbour. And yet, if we tried to go there with the kind of machines we have actually built, the journey would belong less to exploration than to deep time. That contradiction is the quiet doorway into this story. A small red star, invisible to the naked eye, sitting in the Alpha Centauri system, only about 4.25 light-years away. Close enough for astronomers to measure with exquisite care. Close enough for its light to be gathered by telescopes. Close enough that we can speak of planets around it, flares from it, motion across the sky, and its place in our local stellar neighbourhood. But not close enough for a human mission. Not close enough for a probe built like the ones we know. Not close enough for the word near to mean what it means on Earth. So tonight, we are not going to treat Proxima as a destination on a map. We are going to treat it as a ruler. A ruler laid across the first dark step beyond the solar system, showing us how quickly ordinary human distance breaks down. Welcome. I'm glad you're here. Wherever you are listening from, whether the room is dark, the day is ending, or you are letting this play softly in the background, you can settle in. You do not need to hold every number in your mind. You can let the scale arrive slowly. If your eyes are tired, you can close them. If you are still awake and curious, you can follow the light outward, from the sun, past the planets, past the last familiar markers, toward the nearest star we know. And before we drift too far, a small human thing. If this kind of quiet science helps you rest or think, leaving a like is a gentle way to let the channel know. If you want more long, calm journeys through space, time, and the stranger edges of science, you can subscribe and come back whenever the night is ready. And if you feel like it, write in the comments what time it is where you are and where you are listening from. There is something comforting about knowing that other people are hearing the same distant story from bedrooms, trains, apartments, hospitals, and quiet streets all over Earth. Now hold the name Proxima Centauri for a moment. Proxima means nearest. It is an honest name. Among the known stars, this one is the nearest neighbour of the Sun. But language carries a trap. On Earth, nearest is a useful word. The nearest chair is within reach. The nearest town might be a short drive. The nearest country might be a flight away. Even the moon, which once seemed impossibly remote, is close enough that radio voices can cross the gap in a little more than a second. The distance is immense, but still humanly connected. We have sent people there. Their footprints are still in the dust. Proxima belongs to a different category of distance. Its light takes about 4.25 years to reach us. That sounds almost friendly when spoken as time. 4 years is a college degree, a presidential term, a child becoming noticeably older, a season of life that a person can remember. But a light year is not just a poetic unit. It is the distance light travels in 1 year, moving at about 300,000 kilometers every second in vacuum. Every second, light can circle Earth more than 7 times. Every minute, it travels farther than most people will travel in their entire lives. Give light a year, and it crosses nearly 9.46 trillion kilometers. Then give it a little more than 4 years. That is the gap to Proxima. About 40 trillion kilometers. More precisely, current educational summaries often round the distance to about 40.2 trillion kilometers. Another way to say it is about 268,000 times the distance from Earth to the Sun. And the Earth-Sun distance already feels enormous. Sunlight, even moving at light speed, takes about 8 minutes to reach your face on a clear day. That warmth on your skin began its free flight across space before you noticed it. But Proxima is not 8 light minutes away. It is more than 4 light years away. This is where the first assumption breaks. The closest star is not an extension of the solar system. It is not the next island after Neptune. It is not a faraway mountain seen across a valley. Between the outer planets and Proxima, there is not a slightly larger version of the space we already know. There is a change of scale so severe that the solar system becomes, in practical terms, the front porch of a house built beside an open continent of dark. We have crossed parts of that porch. Voyager-1, launched in 1977, is one of the fastest and farthest human-made objects ever sent outward. It has travelled beyond the bubble of the solar wind and into interstellar space, though even that phrase can mislead us. Interstellar space does not mean it is halfway to another star. It means it has passed beyond the sun's immediate protective flow of particles. It is outside the sun's neighbourhood in one sense, but still deep inside the sun's gravitational story. Still nowhere near Proxima in any practical travel sense. Voyager-1 moves at roughly 17 kilometers per second relative to the sun. That is almost impossible to feel from ordinary life. At that speed, it could cross a country in minutes. It could outrun any aeroplane. It is faster than a rifle bullet, faster than the fastest machines most of us will ever see or hear. But against the distance to Proxima, 17 kilometers per second becomes a crawl. That is the strange humiliation of interstellar scale. A machine can become legendary for speed, survive for decades, send back messages from beyond the planets, and still be almost motionless compared with the nearest star. This does not make Voyager small, it makes Proxima honest. The nearest star gives us the first true test of what we mean when we say humans may someday go to the stars. It asks whether we are speaking in symbols or in energy, in dreams or in propulsion, in science fiction time or in the hard arithmetic of kilometers per second. It asks whether a spacecraft is merely something that leaves Earth or something that can survive the long darkness between suns. And for now, the answer is quiet. We can see Proxima, we can measure it, we can name it. We can calculate the delay of its light and infer the presence of worlds around it. We can imagine crossing the distance. But imagination is massless. A spacecraft is not. A spacecraft must be accelerated. It must be powered. It must carry instruments, shielding, guidance, memory, antennas, and some way to remain alive as a machine long after its builders are gone. So the story begins with a correction. Proxima Centauri is close only in the language of stars. In the language of bodies, machines, fuel, signals, and lifetimes, it is still almost unbearably far away. Inside the solar system, distance has a certain mercy. It can be frightening, but it still answers to a human story. Mars is far, but we can send orbiters there. Jupiter is vastly farther, but spacecraft have reached it, photographed its storms, and used its gravity as a kind of invisible hand. Saturn, Uranus, Neptune, each one pushes the boundary outward, but not beyond imagination. We can draw their orbits as rings around the sun. But the solar system flatters us. It gives the impression that space is mostly a matter of patience. A planet is far, so we build a better rocket. A moon is colder, so we design better insulation. A probe needs more time, so we let it sleep and wake. The distances are severe, but the logic remains familiar. You leave one place, you travel through the empty middle, you arrive at another place. Proxima Centauri breaks that rhythm. Not because it is exotic in appearance. In many ways, it is modest. It is a red dwarf, a small, cool, low-mass star. It does not shine like Sirius. From Earth, without a telescope, you cannot see it at all. The nearest star after the Sun is hidden not by secrecy, but by faintness. It is too dim for unaided human eyes, even though it is closer than every other star. That detail matters, because it separates brightness from nearness. We often imagine the night sky as if the brightest things are the most important neighbours. But stars are not lanterns hung at equal distances. A brilliant star may be far away and enormous. A close star may be small and faint. Proxima is nearby in astronomical geography, yet visually absent from ordinary human experience. The closest stellar neighbour does not announce itself. It waits as a point revealed by instruments, a star we know through measurement before sight. The planets move around the Sun in a shared family system. Even Neptune, about 30 times farther from the Sun than Earth is, remains inside a familiar architecture. Light from the Sun reaches Neptune in a little over 4 hours. That is already a staggering delay. A message to a spacecraft near Neptune cannot feel like a phone call. It becomes a command sent into patience. But 4 hours is not 4 years. At Proxima, a radio signal travelling at light speed would need more than 4 years to arrive, and a reply would need more than 4 years to come back. One simple exchange, "Hello, are you functioning? Here is what I saw," would take roughly 8.5 years. Not because the equipment is slow, because the speed limit of the universe itself is now part of the conversation. Inside the solar system, delay is frustrating. Between stars, delay becomes historical. A mission to Mars can be operated with delays of minutes. Rovers cannot be driven like remote-control cars, so they are given sequences, safeguards, and autonomy. But teams on Earth can still live in the same mission rhythm. A problem discovered this week can be studied this week. A new command can arrive soon enough to feel connected. A mission near Proxima would not live in our moment. If a probe arrived and unfolded its instruments beside that faint red star, Earth would not know right away. The news would leave the spacecraft as radio waves, or perhaps laser light, and begin a 4-year return. By the time the first detailed signal reached us, the arrival would already be years old. If something went wrong and we sent instructions back, those instructions would arrive years after the failure began. The machine would need to be not just distant, but self-reliant in a way our current planetary spacecraft only begin to suggest. This is the second broken assumption. Space travel is not only about moving fast enough. It is about being alone long enough. The distance to Proxima turns a spacecraft into a little island of decision-making. It cannot wait for Earth in the way a rover can. It cannot depend on real-time rescue. It cannot assume that the people who built it will still be working when the first results return. If it travels slowly, it may outlast careers, institutions, and political eras. If it travels quickly, it faces different dangers: energy demands, navigation precision, impact hazards, and the difficulty of slowing down when it arrives. Even a flyby is not simple. A spacecraft sent fast enough to cross interstellar distance in a meaningful time may pass through the Proxima system in hours or days after decades of travel. At those speeds, the difference between a successful encounter and a missed one can be a matter of exquisite targeting. A planet is not a stationary dot waiting in the dark. It orbits, the star moves, the spacecraft moves, the entire solar system moves through the galaxy. A mission would have to aim not at where Proxima appears now, but at where the system will be when the spacecraft reaches it. Every long journey is aimed at the future. When we send spacecraft to Mars or Jupiter, mission planners already do this. They launch toward where the planet will be, not where it is. Gravity assists are built from the choreography of moving worlds, but interstellar travel stretches that choreography until prediction, navigation, and correction become part of the central problem. At planetary distances, a correction burn can adjust a path within a mission lifetime. At Proxima distance, every correction carries the weight of years, energy, and communication delay. And then there is the matter of arriving. A popular imagination of star travel often treats reaching a star system like reaching a harbour. The ship crosses the ocean, slows near shore, and begins its visit. But in space, slowing down is as expensive as speeding up. A rocket does not merely need energy to depart, it needs some way to remove velocity at the destination, unless it intends to fly past. For chemical rockets, that usually means carrying propellant. But carrying propellant makes the spacecraft heavier, which means more energy is needed to accelerate it. The rocket equation is not a slogan. It is a wall made of arithmetic. It says, in plain terms, that the faster you want to go by throwing mass backward, the more propellant you need compared with the payload. At ordinary mission speeds, clever staging, gravity assists, and efficient engines can do extraordinary things. But when the desired speed becomes a meaningful fraction of light speed, the fuel problem becomes a different kind of problem entirely. This is why Proxima is so useful as a teacher. It does not need to be the farthest star. It does not need a black hole, a supernova, or a planet made of impossible weather. It only has to be the nearest. The nearest is enough to reveal the shape of the barrier. Because if the closest star is beyond us, then the obstacle is not choosing the right target. The obstacle is the scale of the galaxy itself. The Milky Way contains hundreds of billions of stars, but the first one is already separated from us by a gulf that light crosses in years and machines cross with current technology in ages. That changes the feeling of the night sky. The stars stop being distant decorations and become evidence of a universe where visibility is cheap, but arrival is expensive. You can stand outside on a clear night and let starlight fall into your eyes. Photons from stars cross space freely, without fuel tanks, without life support, without concern for dust, budgets, or time. But a spacecraft is not light. A spacecraft is matter asking permission from physics. And physics answers slowly. For most of human history, the stars were not destinations at all. They were lights, patterns, seasons, warnings, stories. They rose over fields, deserts, oceans, temples, and cold roads. People did not need to know what a star was in order to live by it. The sky turned, the constellations returned, and the world below arranged itself around that rhythm. A star could guide a ship without anyone imagining that the ship might someday try to reach it. That older way of seeing still lives inside us. When we look up, the stars feel placed on a surface. Some are bright, some are dim, but they seem to belong to the same dark ceiling. The mind compresses distance when there is no foreground. A tree on the horizon, a cloud, a planet, a star. At night, all can become part of one flattened scene. Our eyes are excellent at judging the space of bodies, rooms, faces, tools, and nearby ground. They are not built to feel a light year. So the first misunderstanding is not foolish. It is human. The night sky gives almost no natural depth cues. A star twice as far away does not look half as large in any simple way, because stars are unresolved points to our eyes. Brightness can mislead, because a star may look bright either because it is close, or because it is huge and luminous, or both. A small red dwarf nearby can vanish from sight, while a distant blue-white giant can dominate a winter constellation. The sky does not label its distances. It hides three-dimensional space inside points of light. That is why Proxima Centauri had to be measured into nearness. It did not enter human awareness as the obvious neighbour. It had to be found among the faint stars near Alpha Centauri, the brighter pair visible from the southern hemisphere. Alpha Centauri itself appears as one of the brightest stars in Earth's sky, but what the eye sees as a bright point is actually, through telescopes, a stellar system. Alpha Centauri A and B are sun-like stars orbiting one another. Proxima, much dimmer, lies far from them, gravitationally associated with the system. A faint ember at the edge of the family. The nearest star is not the one our eyes would choose. This is a useful humiliation. It reminds us that intuition is local. Human senses evolved for a world where important distances are measured in steps, throws, calls, and days of walking. Even our oldest journeys, across continents and oceans, were still journeys across the surface of one planet. The horizon was far, but it could be reached. A mountain range could be crossed. A sea could be navigated. The moon could be pointed at, dreamed about, and eventually visited. The stars do not fit that inherited grammar. Astronomy had to invent new ways to know distance because the body could not supply them. One of the most important is parallax, a method built from a simple childhood experience. Hold up a finger at arm's length. Close one eye, then the other. The finger appears to jump against the background. The finger has not moved. Your viewpoint has changed. Nearby objects seem to shift more than distant ones. Earth does something similar as it orbits the Sun. 6 months apart, our planet is on opposite sides of its orbit, separated by about 300 million kilometers. That gives astronomers a wide baseline. A nearby star appears to shift by a tiny angle against much more distant background stars. The closer the star, the larger the shift. But even for Proxima, the nearest star, the apparent motion caused by parallax is less than 1 arcsecond. An arcsecond is 1 part of a degree divided by 3,600. It is a sliver of angle so small that the measurement asks for instruments, patience, and careful correction. Nearness at stellar scale is revealed by almost invisible motion. This is one of the quiet beauties of the problem. The closest star is not close enough to feel. It is not close enough to show a disk through ordinary vision. It is not close enough to change the shape of the night by its presence. Its closeness appears as a tiny annual wobble in position, a geometric whisper created by Earth's own motion around the Sun. Once that distance is known, the old map changes. The solar system becomes small in a new way. Not small in beauty, not small in complexity, but small in geography compared with the space between stars. The distance from Earth to the Sun is 1 astronomical unit. Neptune orbits at about 30 astronomical units. The Kuiper belt extends beyond that, with icy bodies moving in the dim outer reaches. Voyager 1 is far beyond the planets, more distant than any operating spacecraft before it. And yet Proxima is about 268,000 astronomical units away. The number is so large that it changes the category. Neptune at 30 astronomical units is remote, cold, and slow. Proxima at hundreds of thousands of astronomical units is not simply farther, it is a different kind of far. If Earth's distance from the Sun were reduced to the width of a small step, Neptune would be across a room or down a hall, depending on the scale. Proxima would not be in the building, it would be miles away, still only the nearest star. This is why diagrams can accidentally lie. A picture of the solar system has to compress emptiness to fit on a page. Planets are drawn too large, orbits too close, stars too decorative. Then a nearby star may be placed at the edge of the same illustration, as if it belongs to a slightly larger neighbourhood. The drawing is not trying to deceive, it is trying to be readable. But readability can quietly distort truth. The universe is not arranged for paper. Even the phrase Alpha Centauri system can make the distance feel tidier than it is. The system sounds bounded and compact, like a set of rooms. But Proxima's relationship to Alpha Centauri A and B is itself stretched across enormous space. It is much closer to them than to us, but still separated from the central pair by a large distance compared with planetary systems. It is a neighbour to those stars, in the loose gravitational language of a stellar triple, not a moon tucked beside a planet. This matters because it prepares the mind for the real subject. The old intuition says distance is an obstacle you overcome by building a faster vehicle. That intuition is not wrong inside ordinary experience. A faster horse, a faster ship, a faster train, a faster aircraft, a faster rocket. Human history is partly the story of collapsing travel times. Oceans shrank, continents shrank. The moon, once mythic, became a place reached in days. So it is natural to imagine the same curve continuing outward. But the curve does not simply continue. At Proxima, speed must be compared not with horses, ships, aircraft, or even Apollo, but with light. And light is not a better rocket. It is the cosmic speed limit for information and massless particles in vacuum. Anything with mass, like a spacecraft, can approach that limit only by paying more and more energy. The faster it goes, the harder each additional gain becomes. The mistake is not hope. The mistake is thinking that interstellar distance is planetary distance with extra zeros. Extra zeros can become a wall. The turning point in this story is that Proxima Centauri is not vague. It is not a mythic star at the edge of an old map. It is not merely one more point in the southern sky. It has been measured, classified, watched, and placed in relation to the Sun, with enough precision that its nearness is not poetic. We know it is near because the sky itself betrays its position year after year, through motion so small that the unaided eye could never use it, but instruments can. That is the strange tension. The star is known well enough to be located, but not reachable enough to be visited. Proxima sits in the constellation Centaurus, in the same broad direction as the bright Alpha Centauri pair. It is a red dwarf, much smaller and cooler than the Sun. Red dwarfs are the most common kind of star in the Milky Way, but they are not the kind that command the eye from across a dark field. They burn slowly, they shine weakly. They can live for extraordinary lengths of time, far longer than stars like the Sun, because they consume their fuel with a kind of cosmic thrift. Proxima's mass is only a fraction of the Sun's. Its radius is also much smaller. Its visible light is so faint that, despite being our closest stellar neighbour, it disappears from the naked eye sky. If you stood outside under perfectly dark conditions and looked toward the region where it lives, you would not see it. The closest star beyond the Sun is not part of ordinary human seeing. It had to be brought into the human world through telescopes and measurement. And then, slowly, it became more than a dot. Astronomers have studied its motion. They have examined its brightness. They have observed flares from its surface. They have detected signs of at least one planet around it, Proxima b, a world whose existence matters not because it gives us a destination, but because it sharpens the ache of distance. The closest star is not empty. It may have worlds. It may have weather made of radiation and charged particles. It may have horizons under a red sun. But those possibilities do not make it easier to reach. In fact, they make the problem feel more exact. A purely imaginary star can remain safely unreachable in a story. A measured star becomes worse. It has coordinates, it has a distance, it has a spectrum, it has a mass, it has a family. The more real Proxima becomes, the more uncomfortable the distance becomes, because now we are not separated from an abstraction, we are separated from something specific. This is where astronomy and engineering begin to part ways. Astronomy is extraordinarily good at receiving. It waits for light. It measures tiny shifts. It stretches human perception through mirrors, detectors, timing, and mathematics. A telescope does not need to cross the gap to learn from a star. It only needs the star's photons to arrive. Those photons have already paid the travel cost. They left Proxima years ago, crossed the darkness without engines, and struck our instruments as evidence. Engineering is different. Engineering does not receive the universe for free. It asks a machine to go there, and a machine has mass. It must be launched from a planet, accelerated away from the Sun, guided over an immense trajectory, protected from hazards, kept powered, and made capable of doing useful work at the far end. Every kilogram matters. Every instrument matters. Every shield, antenna, battery, computer, and structural support adds to the burden that must be moved. This is why the discovery of a nearby star does not automatically create a mission. A telescope can turn patience into knowledge. A spacecraft must turn energy into motion. Consider how much success we already celebrate inside the solar system. Reaching Mars is difficult. Missions fail, landings go wrong, dust storms, thermal stress, communication delay, and mechanical wear all matter. Reaching Jupiter requires years and careful trajectories. Reaching Saturn is an epic. Reaching Pluto took New Horizons more than 9 years, even though Pluto is still part of our solar system's outer architecture. New Horizons was fast. It left Earth in 2006 and flew past Pluto in 2015, giving humanity its first close view of a world that had been mostly a blur. That journey was one of the great acts of modern exploration, and yet the distance to Pluto is tiny compared with the distance to Proxima. Pluto varies in distance as it orbits the Sun, but it lies tens of astronomical units away. Proxima lies hundreds of thousands of astronomical units away. The numbers do not scale gently. They tear the map. If a spacecraft can cross the distance to Pluto in under a decade, it does not follow that it can cross the distance to Proxima in a few centuries. The gap is not one more outer planet. It is not the next belt beyond the belt. It is the first true interval between suns. The solar system has objects arranged within the gravitational realm of one star. Interstellar space is the emptiness between those realms, and that emptiness is larger than the architecture it separates. The turning point, then, is not only that Proxima is close, it is that closeness loses its old meaning. When astronomers say Proxima is the closest star, they are speaking in the scale of the Milky Way. In that scale, 4.25 light-years is next door. The galaxy itself is about 100,000 light-years across, depending on how one defines its faint outer structure. Against that span, Proxima is local. It belongs to the Sun's immediate stellar neighbourhood. It is so close, by galactic standards, that it helps define where we are. But a human body does not live at galactic scale. A human body lives by pulse, breath, sleep, hunger, injury, temperature, and age. A human mission lives by launch windows, funding cycles, crew health, life support reliability, and the decay of machines. A civilization may dream in centuries, but engineers must still build in materials. The scale of the galaxy may call Proxima near. The scale of a life calls it beyond the wall. This distinction protects the truth of the title. Proxima is not unreachable because it is far compared with everything. It is reachable by light. It is reachable by measurement. It is reachable by imagination, mathematics, and perhaps one day by a kind of probe very different from the spacecraft we know. But it is out of human reach now, because reach is not the same as awareness. A hand can reach only so far. An eye can reach much farther. A telescope reaches farther still. But a spacecraft must carry its reach with it, kilogram by kilogram, second by second, through a darkness that does not become smaller because we have named what waits beyond it. And that is why Proxima becomes almost tender as a scientific object. It is both the nearest invitation and the first refusal. It says, yes, the stars are real places. Yes, they have distances, motions, spectra, and worlds. Yes, the nearest one is known. And still, the universe has placed even this first known neighbour at a distance that exposes the difference between knowing where something is and having any practical way to arrive. The next question is no longer where Proxima is. The next question is what it would cost to move matter toward it fast enough for the journey to belong to us. To understand why Proxima is out of reach, we have to give up a comforting picture of travel. On Earth, travel is often imagined as distance divided by speed. If a place is far away, you go faster. If the journey is too long, you build a better vehicle. A walking road becomes a rail line. A sailing route becomes a flight path. A flight path becomes a rocket trajectory. The pattern seems obvious because, for much of human history, it has worked. But rockets do not merely move through distance. They spend mass to change motion. That one fact changes everything. A car can push against a road, a train can push against rails, a ship can push against water, an airplane can push against air. A rocket in space has almost nothing outside itself to push against, so it carries the thing it will throw backward. Propellant leaves the engine at high speed in one direction, and the spacecraft gains speed in the other. This is not a trick. It is conservation of momentum, one of the plainest and most unforgiving rules in physics. To move forward, the rocket must send something backward. The difficulty is that the propellant must be carried before it can be used. At launch, a rocket is not only carrying its payload, it is carrying the propellant needed for later, and often the propellant needed to accelerate the propellant needed for later. This is why rockets are mostly fuel at the beginning and much smaller machines by the end. They are staged, they drop empty tanks and engines, they become lighter as they climb. Even reaching orbit around Earth is an act of careful shedding, a controlled surrender of mass. Interstellar travel pushes this logic until it becomes brutal. If a spacecraft is going only to the Moon, a few days of travel can be enough. If it is going to Mars, months are possible with current chemical propulsion. If it is going to Jupiter or Saturn, the mission stretches into years, often using gravity assists to steal tiny changes in speed and direction from planets. But Proxima is not months or years away at ordinary spacecraft speeds. It is tens of trillions of kilometers away. So the obvious response is, go faster. The problem is that faster is expensive. Not expensive only in money, although it would be that too. Expensive in energy, expensive in propellant, expensive in heat, expensive in structure, expensive in risk. A spacecraft moving twice as fast does not simply need twice the kinetic energy. Kinetic energy grows with the square of speed. Double the speed, and the energy of motion becomes 4 times larger. 10 times the speed, and the energy becomes 100 times larger. This is before we even ask how efficiently the engine can convert stored energy into useful motion. That square hides quietly inside every dream of the stars. Voyager 1 moves at about 17 kilometers per second relative to the Sun. That is fast enough to feel almost unreal by Earth standards. But light moves at about 300,000 kilometers per second. Voyager is moving at only a tiny fraction of light speed, roughly 5/10,000ths of 1%. At that pace, a Proxima-like crossing is not a mission you assign to a crew, or even to one generation of engineers. It becomes a message in a bottle aimed into deep time. If we wanted a spacecraft to reach Proxima in about a human lifetime, say in a few decades, it would need to move at a meaningful fraction of light speed. Even 1/10 the speed of light would be 30,000 kilometers per second. That is not merely faster than Voyager, it is thousands of times faster. And because energy grows with speed squared, the energy challenge does not rise politely, it explodes upward. Then comes the second half of the problem. Arrival is not the same as passing by. A spacecraft that races toward Proxima at a large fraction of light speed might cross the distance in a timescale that sounds human. But if it cannot slow down, it becomes a brief flash through the system. It may have only hours or days to observe targets after decades of flight. To enter orbit around Proxima, or around a planet there, it must lose an enormous amount of speed. In rocketry, slowing down usually requires propulsion too. You must spend energy and propellant not only to leave, but to arrive. This is the hidden cost many imagined journeys forget. The train slows by friction and brakes against rails. A ship slows against water. An aircraft slows against air. But in interstellar space, there is no friendly medium waiting to catch you. A spacecraft arrives with all the speed it carried across the gap. If it has no way to brake, the destination becomes not a harbour, but a blur. For a crewed mission, that problem becomes even less forgiving. A human spacecraft cannot be a thin instrument package with a transmitter. It must carry people. People need air, water, food, temperature control, radiation protection, waste recycling, medical care, and some form of psychological endurance. The payload mass increases. More mass demands more energy to accelerate. More shielding protects the crew, but also makes the vehicle heavier. More life support makes survival possible, but also increases the burden. In interstellar flight, kindness to the body becomes weight, and weight becomes energy. Even robotic probes face the same law in smaller form. A camera has mass, a computer has mass, an antenna has mass, a power source has mass, a dust shield has mass, a structure strong enough to survive acceleration has mass, a navigation system has mass. There is no purely abstract spacecraft. Every capability must be physically carried. The universe charges for every gram. This is why advanced concepts often try to escape the ordinary rocket pattern. If a spacecraft does not carry all its energy and propellant, the problem changes. A solar sail uses light pressure from the sun, but sunlight weakens with distance and becomes too faint for deep acceleration far from the sun. A laser sail imagines powerful beams from near Earth or elsewhere, pushing an extremely lightweight sail to high speed. In such a concept, the energy source stays behind, and the craft can be very small. This is one reason laser-driven microprobe ideas are taken seriously as a possible route to much faster interstellar flybys. But a microprobe is not a starship. A gram-scale or kilogram-scale probe, moving at a fraction of light speed, is a profoundly different thing from a crewed vessel. It may not slow down. It must survive acceleration, aim precisely, endure dust impacts at terrifying relative speeds, collect useful data quickly, and send a faint signal back across 4.25 light-years. The idea is not fantasy in the empty sense, it rests on real physics, but the engineering gap between a concept and a working interstellar mission is enormous. So the first core mechanism is not simply rockets are too slow. It is that motion itself has a price. To reach Proxima, matter must be accelerated across a distance so large that ordinary spacecraft speeds turn into geological patience. To make the journey humanly short, the spacecraft must move so fast that energy, braking, shielding, navigation and communication become dominant problems. And if humans are aboard, the spacecraft must become not just an arrow, but a world, sealed, protected, powered, repaired, and livable, across a journey no human society has ever attempted. This is what Proxima reveals. It is not guarded by an enemy. It is not hidden behind a forbidden boundary. There is no wall in space with the word impossible written on it. There is only distance, mass, energy, and time. And they are enough. A number like 40 trillion kilometers is too large to enter the mind all at once. It arrives as sound, not meaning. 40 trillion. The words pass quickly. They can be spoken in less than 2 seconds. But the distance they describe would swallow every journey humanity has ever made. Every road, every migration, every orbit, every ocean crossing, every aircraft route, every mission to the moon, every probe sent toward the planets, and still remain almost untouched. So we have to slow the number down. Start with the Earth and the Sun. The average distance between them is 1 astronomical unit, about 150 million kilometers. This is already not a human distance. If you could drive a car upward through space at highway speed, never stopping, never turning, never breaking down, the trip to the Sun would last far longer than any ordinary life. But light crosses that same span in about 8 minutes and 20 seconds. That is why sunlight feels immediate, even though it is not. The Sun you see has already happened. Its light left before your thought about it did. Now move outward. Mars, at its closest, is still many light minutes away. Jupiter is tens of light minutes away. Neptune is light hours away. A signal sent to the outer planets must be planned with patience, because no one can talk to a spacecraft there in the way people talk across a room. Still, these delays fit inside a day. You can send a command in the morning and, depending on the destination, receive some answer later in the same human rhythm of meals, sleep, and weather. Proxima does not fit inside a day. It does not fit inside a week, or a month, or a year. Light needs about 4.25 years to cross from Proxima to Earth. If Proxima brightened in some dramatic way tonight, we would not learn of it tonight. We would learn years later, when the light from that event finally arrived. And if we sent a message toward a probe near Proxima, the command would travel outward for more than 4 years before touching the spacecraft. Any answer would travel back for more than 4 years more. One exchange becomes a slice of childhood. A question sent when a child begins school might return when that child is nearly a teenager. That is the gentlest version of the distance, because light is doing the travelling. Machines move differently. Take Voyager 1, not because it is aimed at Proxima, but because it gives us a real human-made speed instead of a fantasy speed, roughly 17 kilometers every second. In 1 second, Voyager covers more distance than most people commute in a day. In a minute, it travels about 1,000 kilometers. In an hour, it crosses more than 60,000 kilometers. In a day, it moves more than 1 million kilometers. By Earth standards, it is astonishing. But Proxima does not care about Earth standards. At 1 million kilometers per day, even 40 trillion kilometers remains a monstrous distance. Divide the distance by the speed, and the journey becomes tens of thousands of years. The exact number depends on assumptions, because spacecraft velocity is measured relative to particular objects, and trajectories are not straight lines drawn in a schoolbook. But the order of magnitude is clear. Voyager-like speed turns Proxima into a destination roughly 70,000 years away. 70,000 years is not a long mission. It is older than agriculture, older than cities, older than writing. It reaches back toward a time when modern humans were alive, but the world they inhabited was not the world of nations, books, telescopes, engines, or maps of the galaxy. If a spacecraft had been launched toward Proxima at Voyager-like speed during that deep human past, its builders would not have had metal tools in the usual sense. They would not have known Earth was a planet. They would not have known what a star was. And only now, after the rise and fall of languages and civilizations, would the machine be approaching the nearest star. That is what current speed means when placed against stellar distance. A faster comparison changes the feeling, but not the problem. New Horizons reached Pluto in under 10 years, but Pluto is not a star. Its distance is counted in tens of astronomical units, not hundreds of thousands. Parker Solar Probe, diving close to the Sun, reaches extraordinary speeds compared with human machines, far faster than Voyager at points in its orbit, because it falls deep into the Sun's gravity. But its speed is part of an inner solar system dance, not a simple outward cruise to another star. Speed records can inspire, but they do not erase the energy and trajectory problem of crossing light years. And so the mind reaches for percentages of light speed. 1% of light speed sounds almost modest. Not 10%, not half, just 1%. But 1% of light speed is about 3,000 kilometers per second. That is already far beyond the cruise speeds of ordinary deep space probes. At 1% of light speed, a crossing to Proxima would still take more than 4 centuries, ignoring acceleration and deceleration. 4 centuries is shorter than 70,000 years, but it is still longer than any institution has kept a spacecraft alive, longer than modern science has existed in its present form, longer than many nations have survived in recognizable shape. At 10% of light speed, Proxima becomes a journey of decades rather than centuries, again in a simplified flyby sense. Now the number begins to sound almost human. 40-something years. A person could be born near launch and be alive when the craft arrives. But 10% of light speed is about 30,000 kilometers per second. At that speed, even dust becomes dangerous. A tiny grain in the path is no longer a speck, it is a high-energy impact event. Space is emptier than any vacuum we can make on Earth, but over trillions of kilometers, emptiness still contains particles, dust, gas, and uncertainty. The faster you go, the more the darkness becomes weather. A slow spacecraft fears time. A fast spacecraft fears collision, heat, targeting error, and the violence hidden inside its own speed. There is no free version of the journey. Patience pays in centuries. Speed pays in energy and risk. A crewed spacecraft pays in all of these, plus the needs of living bodies. Now bring the scale back down to a room. Imagine a map where the Sun is a small glowing bead in your hand. Earth is a speck less than a step away. Neptune might be across the house. The outer spacecraft are somewhere beyond the yard. On that same scale, Proxima is not at the next table. It is not across the street. It is far beyond the neighborhood. The nearest star has moved out of the map you thought you were holding. This is why interstellar distance has a special cruelty. It lets us see the target clearly enough to want it. It lets us calculate the journey clearly enough to understand why we cannot yet make it. The number 4.25 light-years is compact. The reality behind it is not. It is a measurement of space, but also of delay, energy, risk, and human smallness. It tells us that the universe is not merely large in the way an ocean is large. An ocean resists us, but it still belongs to the scale of bodies and vessels. Proxima belongs to the scale where even our fastest artifacts begin to resemble drifting seeds. And still, that faint red star is the closest one. That is the part that stays with you. Not that the universe becomes unreachable at its far edge, but that unreachable begins at the first doorstep beyond the Sun. The first explanation is speed. But speed is not enough. A spacecraft could be imagined moving faster than any probe we have ever built, faster than Voyager, faster than New Horizons, faster than the fastest solar diving machines. We could let the mind accelerate it until the travel time begins to feel less impossible. A century, 50 years, 20 years in the most ambitious concepts. The numbers become thrilling. They begin to sound like a future that might fit inside history rather than geology. And then the second layer appears. The spacecraft has to survive the journey. Not for a dramatic launch sequence, not for a few minutes of flame and thunder, not only through the cold around Earth, or the radiation belts, or the long quiet between planets. It has to survive years, decades, centuries, or longer, depending on speed, in a region where there is no maintenance bay, no rescue crew, no spare part, no hand reaching in from outside the story. Human engineering is impressive, but it is also intimate. Machines fail in small ways before they fail in large ones. A circuit degrades, a valve sticks, a wire cracks, a lubricant changes, a sensor drifts, a bit flips in memory, a heater draws too much power, a battery ages, a micrometeoroid strikes the wrong place. On Earth, failure often becomes repair. In interstellar space, failure becomes fate, unless the machine has already been designed around it. This is why long-duration missions are not merely short missions extended. They become a different discipline. Voyager is again a useful teacher, because its success is real and humbling. Launched in 1977, the Voyager spacecraft have lasted for decades, far beyond their original planetary encounters. They crossed the outer solar system, visited giant planets, and continued sending data as their power slowly declined. Their radioisotope thermoelectric generators convert heat from radioactive decay into electricity. That decay is steady and dependable, but it also means available power falls with time. Engineers have had to turn off instruments and heaters, manage dwindling resources, and preserve communication with spacecraft built in another era of computing. This is one of the most beautiful engineering stories we have. But it also shows the limit. A few decades is heroic for a spacecraft. Proxima, at current speeds, asks for timescales far beyond that. Even if a future probe were fast enough to arrive within decades, it would still need to keep its systems stable through a journey longer than most spacecraft missions, then wake, navigate, observe, process data, and transmit across more than 4 light years. The hardest part might not be leaving. It might be arriving still capable of speech. Power is only one problem. The interstellar medium is thin, but it is not nothing. Space between stars contains gas, dust grains, charged particles, magnetic fields, and radiation. Its density is extraordinarily low compared with air, but over trillions of kilometers, even rare matter matters. A slow spacecraft may encounter particles gently, one by one, across long ages. A fast spacecraft meets them with violence. At a significant fraction of light speed, a tiny dust grain can strike with destructive energy because the relative velocity is enormous. Something too small to see can become an impact hazard simply because speed has turned it into a bullet. This changes the meaning of emptiness. On Earth, emptiness sounds safe. An empty road has no traffic, an empty room has no obstacle. But at interstellar speed, empty space is a statistical environment. The danger is not that it is crowded. The danger is that the journey is so long and the velocity so high that even rare encounters must be taken seriously. Shielding becomes necessary. But shielding adds mass. Added mass demands more energy. More energy may require a larger propulsion system. The mission begins to fold back on itself. Radiation adds another pressure. A robotic probe can tolerate more radiation than a human body, but electronics are not immune. Charged particles can damage materials, degrade sensors, and disrupt memory. Cosmic rays can penetrate shielding and produce errors in electronic systems. Spacecraft already use hardened components, redundancy, error correction, and careful design to survive harsh environments around planets and in deep space. But interstellar missions would require reliability over extreme durations and possibly extreme speeds, with no chance to replace weakened parts. If humans were aboard, radiation would become far more severe. Outside Earth's magnetic field and atmosphere, the body is exposed to high-energy particles from the Sun and from beyond the solar system. A crewed interstellar mission would need shielding sufficient not for days or months, but for years or decades. That shielding might involve mass, water, fuel, or specialized materials. Whatever the solution, it would not be weightless. The human body makes the starship heavier because biology asks for protection. Then comes navigation. Proxima is not a target painted on a wall. It is moving through space. The Sun is moving too. The spacecraft itself begins inside a moving solar system and travels across a gravitational landscape shaped by the Sun, planets, and, eventually, the target star system. Over years or decades, tiny errors grow. A small miscalculation early in flight can become a vast miss later. Course corrections are possible, but they require propellant, power, sensors, and decisions. And if communication takes years, the spacecraft cannot rely on Earth for every adjustment. At interstellar distance, navigation becomes a form of memory. The probe must know where it is, where it has been, where the target will be, and how to correct itself with limited resources. It may use star trackers, inertial systems, optical navigation, pulsar timing in some concepts, or observations of the target system as it approaches. But all of these require working instruments. The mission depends on a chain of functioning parts that must remain trustworthy after the long silence of cruise. There is also the question of data. A spacecraft that reaches Proxima but cannot report home has not completed the mission in any meaningful scientific sense. It must send information across 4.25 light-years. Radio signals spread out as they travel, becoming weaker with distance. Lasers can be narrower, but require extreme pointing accuracy. A transmitter near Proxima must aim at a moving Earth, or at least toward the solar system, across a distance so large that a slight pointing error could waste the signal into darkness. The receiving side must listen with patient, sensitive instruments, perhaps for faint whispers from a tiny machine older than many of the people who hear it. This is where the romance of interstellar travel becomes almost unbearably delicate. The mission is not just a launch and the destination. It is a chain. Acceleration, survival, navigation, observation, transmission, reception, interpretation. Break any link, and the star remains unvisited in practice, even if some piece of human metal once crossed the distance. So Proxima's difficulty is layered. First, the distance is enormous. Then the speed required is extreme. Then the energy becomes punishing. Then arrival demands braking or accepts a brief flyby. Then the spacecraft must survive dust, radiation, aging, power loss, and navigation drift. Then, after all that, it must speak back across 4 years of light time with a voice faint enough that Earth must learn how to hear it. This is why the nearest star feels almost quiet in its refusal. It does not forbid us with drama. It simply asks every system to keep working after Earth is too far away to help. The deeper shift comes when we stop asking how far Proxima is and start asking what kind of journey Proxima would require. Because the answer is not simply a longer version of the journeys we already know. A journey to Mars is dangerous, but it still belongs to mission time. A crew launches, travels for months, arrives while the launch is still part of living memory, and remains close enough for Earth to follow the mission as an unfolding event. Even the outer planets, though distant, are still visited by spacecraft whose makers can watch the data return within a professional lifetime. A graduate student can become a mission scientist. A mission scientist can grow old with the spacecraft. The work remains humanly threaded. Proxima threatens to cut that thread. If a spacecraft moves slowly, it would become a project across deep history. If it moved quickly, it would become a project at the edge of our energy, materials, and guidance abilities. Either way, the mission stops resembling an expedition and begins to resemble a promise made by one generation to another that may never meet it. This is the midpoint of the story. The nearest star does not only test our rockets. It tests whether exploration can survive beyond the scale of a human life. We are used to thinking of exploration as arrival. A ship appears at a shore, a rover rolls onto Martian soil, a lander touches down on a moon. The explorer and the destination exist together in the same narrative moment. Someone leaves, someone arrives, someone receives the news. Even when the message is delayed, the story remains connected. But Proxima stretches the story until cause and effect are separated by years, decades, maybe centuries. A command becomes an artifact of the past. A signal becomes a ghost of an old event. Arrival, if it happens, may not feel like arrival to those who launched the spacecraft. It may feel like archaeology. Future people listening to a machine built by their predecessors, receiving data from a probe that began its journey under a different sky of culture, technology, and memory. There is a quiet reversal here. Inside the solar system, distance turns engineers into navigators. Between stars, distance turns engineers into ancestors. That sentence is not metaphor only, it is a practical mission constraint. To design something for Proxima, one must design not just a spacecraft, but a continuity of listening. Ground stations must exist, or their successors must. Data formats must be interpretable. Mission knowledge must be preserved. The receiving civilization must remember what it sent, why it sent it, and how to understand whatever comes back. A spacecraft can fail from radiation, but a mission can also fail from forgetting. This may sound philosophical, but it is also technical. Long missions already face this on smaller scales. Voyager's computers, instruments, and communication systems came from the 1970s. Engineers today manage spacecraft older than many of the people working on them. Documentation, institutional memory, and careful interpretation matter. Commands must be written for hardware with severe limits by modern standards. The spacecraft are not just far away, they are old. A Proxima mission would magnify that problem enormously. If it were a slow probe, the technological culture that receives it could be unrecognizable. If it were a fast probe, the design pressures become savage. Miniaturization, thermal control, radiation hardness, shielding, pointing, autonomy, data compression, power management, and perhaps braking or flyby timing. The mission becomes not one heroic difficulty, but a whole stack of them, each connected to the others. Now consider the target itself. Proxima is not a gentle substitute for the Sun. It is a red dwarf, smaller and cooler, but it can produce powerful flares. Red dwarfs often have strong magnetic activity, especially when young, and flares can bathe nearby planets in radiation. Because red dwarfs are dim, any planet warm enough for liquid water on its surface would need to orbit much closer to the star than Earth orbits the Sun. Proxima b, the best-known planet candidate in that system, orbits close to Proxima, with a period of about 11 days. That does not mean it is habitable in the simple, comfortable sense. It means the question is complicated. Again, the title sharpens. Even if we cross the distance, we would not arrive at a second Earth waiting under familiar sunlight. We would arrive near a faint, active red star, in a system where close-in planets may face stellar flares, possible atmospheric erosion, tidal effects, and conditions still debated from afar. The destination is scientifically rich, but not easy. The nearest star does not offer a soft landing for human imagination. It offers a real environment, and real environments have consequences. This matters because science fiction often gives us stars as backdrops and planets as stages. Astronomy gives us systems. A star's mass shapes its planet's orbits. Its brightness shapes their temperatures. Its magnetic behavior shapes their radiation environment. Its age shapes the history of any atmosphere or surface. Its flares can alter chemistry. Its gravity rules the motion of everything nearby. To go to Proxima would not be to step into a symbolic nearest star. It would be to enter a physical neighborhood governed by a red dwarf's nature. That is a different kind of desire. not simply to go because it is there, but to know because it is specific. And perhaps this is why Proxima holds such power. It is close enough to be studied in detail, compared with more distant stars. It is close enough that a planet detection can make headlines. It is close enough that serious people can discuss whether a future robotic flyby might someday be attempted by methods unlike ordinary rockets. Yet it remains far enough to expose every weakness in our present ability to move through space. It lives exactly at the boundary between knowledge and reach. Too close to ignore. Too far to touch. This boundary may be more important than Proxima itself. Every technological civilization, if such civilizations exist elsewhere, would face some version of this boundary. The nearest star would become the first test, not the grand crossing of the galaxy, not the leap to the center of the Milky Way, just the first neighbor, the first light beyond the home star, the first chance to learn whether intelligence can turn curiosity into motion across interstellar space. For now, our answer is partial. We have turned curiosity into sight. We have built instruments that can measure the tiny shift of stars, detect the wobble or dimming that may reveal planets, analyze light to infer temperature and composition, and send robotic emissaries beyond the planets. That is not nothing. It is extraordinary. A species of primates on one rocky world has learned the distance to the nearest star. But we have not yet turned that knowledge into a rival. The midpoint reversal is gentle but severe. Proxima is not a destination delayed by lack of effort. It is a mirror showing us the current shape of our civilization. We are good at seeing. We are learning to send. We are not yet good at crossing the first true gulf. The nearest star is not the beginning of easy expansion. It is the place where expansion becomes honest. The most trustworthy part of Proxima's story is also the quietest. No one has gone there. No probe has flown past it. No camera has looked back from its neighborhood and shown the sun as a distant star. Everything we know about Proxima has come across the gap without our bodies crossing it. Light has done the traveling. Instruments have done the waiting. Mathematics has done the translation. That matters because the distance is not a guess made from wonder. It is a measurement. The foundation is parallax, the small apparent shift of a nearby star against the much farther background as Earth moves around the Sun. In January, Earth views the sky from one side of its orbit. 6 months later, it views the sky from the opposite side. That baseline is about 300 million kilometers wide. For ordinary human thinking, 300 million kilometers is immense. For measuring the nearest stars, it is just barely enough to create a tiny angle. Proxima's parallax is less than an arcsecond. An arcsecond is 1/60th of an arcminute, and 1 arcminute is 1/60th of a degree. If a full circle has 360 degrees, then an arcsecond is a very small shaving of the sky. Measuring a star's annual shift at that scale is like trying to infer the shape of a vast landscape from the smallest tremble in a distant point of light. It requires stable instruments, repeated observation, and corrections for other kinds of motion. Because stars do not sit still. Proxima has proper motion, its real drift across the sky as it moves through the galaxy relative to us. It also has radial motion, the component of its movement toward or away from us, measured through the Doppler shift in its light. If a star's spectral lines shift slightly toward longer wavelengths, it is moving away along our line of sight. If they shift toward shorter wavelengths, it is moving toward us. These shifts are tiny, but light carries them faithfully. A star's motion becomes written into the stretching or compression of its spectrum. A spectrum is not just colour. It is a fingerprint made of missing and bright lines. Atoms and molecules absorb or emit light at specific wavelengths. When astronomers spread starlight into its component wavelengths, they can infer temperature, composition, motion, magnetic activity, and sometimes the influence of orbiting planets. For Proxima, spectroscopy helps reveal its red dwarf nature, cool and faint compared with the Sun, but physically active, capable of flares that can change its brightness and radiation environment. This is how a star becomes known without being touched. not by one kind of evidence, but by many. Position on the sky, tiny parallax shift, proper motion, spectral type, brightness, variability, radial velocity. Each measurement is limited, but together they make a physical portrait. Proxima is not merely the closest star, as a phrase repeated in textbooks. It is an object whose distance, motion, and nature are constrained by observation. And then came the planets. The strongest evidence for Proxima b came through radial velocity measurements. A planet does not only orbit a star, the star also moves slightly in response, because both bodies orbit their shared centre of mass. For a small planet around a small star, this stellar wobble can be subtle, but detectable if observations are precise and repeated. Proxima b was reported as a planet candidate with an orbital period of about 11.2 days, implying a close orbit around the faint red dwarf. That closeness is important because a red dwarf's habitable zone, where temperatures might allow liquid water under the right atmospheric conditions, lies much nearer the star than Earth lies to the Sun. But here the uncertainty must be kept clean. A planet in a habitable zone is not the same thing as a habitable planet. The phrase habitable zone means a range of orbital distances where, with suitable atmospheric pressure and composition, liquid water could exist on a rocky surface. It does not guarantee an atmosphere. It does not guarantee oceans. It does not guarantee life. Around an active red dwarf, flares and high-energy radiation may threaten atmospheres, alter chemistry, and complicate surface conditions. Tidal locking may also matter, because a close-in planet can rotate in a way that keeps one side facing the star. Whether such a world could maintain stable, life-friendly conditions depends on atmosphere, magnetic environment, volatile history, geology, and many other factors we cannot yet directly inspect in detail. This is why evidence must be separated from desire. We know Proxima is near, by stellar standards. We know it is a red dwarf. We have strong evidence for at least one planet. We can estimate orbital properties. We can model possible climates. We can discuss flares and radiation. But we cannot claim that Proxima b is Earth-like in the comfortable sense. We cannot claim it has life. We cannot claim it is waiting for us. The evidence is enough to make it scientifically precious. It is not enough to make it a second home. There have also been observations of Proxima's flare activity. Red dwarfs can release bursts of energy from magnetic processes in their outer layers. A flare can brighten the star and increase ultraviolet and X-ray radiation. For any close planet, this matters. A planet near a red dwarf may receive enough average energy to sit in a temperature range of interest, while also being exposed to a harsher radiation environment than the gentle phrase habitable zone suggests. The same star that makes close orbit warmth possible can also make close orbit survival complicated. Again, the star refuses simplicity. The evidence path gives us both intimacy and distance. We know enough to name details. We do not know enough to tell a clean story of arrival, oceans, skies, and life. That uncertainty is not a weakness in science. It is one of science's main forms of honesty. It marks the boundary between what the instruments have actually shown and what the imagination would like to place there. Even the distance measurement carries that feeling. Parallax tells us where Proxima is. Spectra tell us what kind of star it is. Radial velocity suggests the tug of a planet. Photometry reveals changes in brightness. Models help interpret the environment. But none of these methods moves a spacecraft 1 meter closer. The knowledge crosses the gap because light can cross it. Our machines remain at home. This is a strange achievement. We have built a civilization capable of measuring the nearest star to astonishing precision, detecting the faint gravitational hint of a planet around it, and debating the atmospheric future of a world no human eye has seen directly. That is not failure. That is a triumph of remote knowing. But it is a triumph that also reveals the limit of touch. Proxima is therefore not unknown. It is known in the way astronomy knows, indirectly, patiently, through signals that have survived years of travel. The star has already sent us everything we have learned from it. Its light left, crossed the dark, entered our telescopes, and became numbers, graphs, papers, models, and quiet human understanding. But every one of those photons came to us. We did not go to them. And that difference is the heart of the distance. The honest version of this story must leave room for the future. It would be easy to say that Proxima Centauri is impossible to reach. The sentence has force. It sounds clean. It gives the mind a hard edge to hold. But science is careful with words like impossible, because impossible belongs to laws, not merely to difficulty. Faster than light travel, as far as our current understanding goes, is forbidden for ordinary objects by the structure of relativity. But reaching Proxima more slowly than light is not forbidden in that same way. Physics does not place a locked door between the Sun and its nearest stellar neighbour. The door is open. It is just unbelievably far away. That distinction matters. Proxima is out of human reach with the kinds of spacecraft we have built, and with the mission architectures we know how to operate reliably today. It is not out of all conceivable reach for all future technology. A tiny robotic probe, accelerated by methods unlike ordinary rockets, may someday attempt some form of interstellar flyby. A future civilization with far larger energy systems, different propulsion, better materials, and deeper patience might do things that would seem almost dreamlike now. But possibility is not the same as readiness. This is the line the script must walk. There are several families of ideas for crossing interstellar distance. Chemical rockets, the kind that carried humans to the moon and launched most spacecraft from Earth, are powerful but not suited to pushing large payloads to meaningful fractions of light speed. Their exhaust velocities and propellant requirements make the journey to Proxima impossibly long for practical human purposes. Nuclear thermal or nuclear electric propulsion could improve some kinds of deep space travel. But even these do not magically turn light years into ordinary mission distances. They may change solar system exploration before they change interstellar exploration. Fusion propulsion appears more tempting. Fusion powers the stars themselves, including Proxima. In principle, fusion can release far more energy per unit mass than chemical reactions. A spacecraft using controlled fusion might reach much higher speeds than today's probes, at least in concept. But controlled fusion as a compact, reliable spacecraft propulsion system remains far beyond present mission readiness. It is not enough to say fusion has energy. The energy must be controlled, directed, contained, converted into thrust, kept stable, and carried or gathered in a form that works for a vehicle travelling through deep space. The mechanism matters. A propulsion concept is not a magic word. It needs a power source, a reaction mass or momentum exchange, heat management, structural strength, guidance, and a mission profile. Waste heat must go somewhere. Engines must survive their own operation. The spacecraft must carry equipment that does not erase the speed advantage by becoming too massive. Every attractive idea has to pass through the same narrowing gate. What can be built? What can be powered? What can be controlled? And what can survive? Antimatter is even more extreme. Matter and antimatter annihilation can release enormous energy, far beyond chemical fuel and even beyond fusion per unit mass. This makes antimatter a recurring dream in discussions of starflight, but antimatter is not available as a practical fuel. It is extraordinarily difficult to produce in useful amounts, difficult to store, and dangerous in ways that turn the engineering problem into something almost absurd by present standards. Calling antimatter powerful is true. Calling it a practical route to Proxima today would be misleading. Then there are sails. Sails are compelling because they loosen the grip of the rocket equation. A sail does not need to throw onboard propellant backward in the ordinary way. It can be pushed by light. Sunlight can push a reflective sail very gently. Lasers could, in principle, push one much harder if an enormous beam system were built and controlled. This is why laser-driven microprobe ideas have received serious attention. A tiny craft attached to a very light sail might be accelerated to a significant fraction of light speed by powerful lasers from the solar system. This changes the problem, but does not erase it. The spacecraft would have to be extremely light. The sail would have to survive intense illumination and acceleration. The beam would have to remain focused and accurately aimed over large distances during the acceleration phase. The probe would need to survive interstellar dust at tremendous speed. It would probably fly past Proxima rather than stop. During that brief encounter, it would have to collect useful data and then send information back across more than 4 light years. Perhaps with a transmitter so small that even hearing it would be an achievement. A laser sail can make Proxima feel imaginable. It does not make Proxima easy. There are also slower, more patient ideas. Generation ships, world ships, suspended animation, embryo missions, self-repairing robotic craft, or artificial habitats that do not try to make the journey short. These belong partly to engineering speculation and partly to cultural imagination. Some do not violate basic physics, but they introduce other enormous questions. How do you maintain a closed ecosystem for centuries? How do you protect generations from radiation, failure, conflict, disease, and social collapse? How do you justify sending people who did not choose the original mission? How do you preserve meaning when the destination belongs to descendants? For a sleep-friendly science documentary, those ideas can be named, but not treated as solved. They are not current mission plans in the ordinary sense. They are thought experiments about what might be required if biology itself crossed the gap slowly. They show that interstellar travel is not only a propulsion problem, it is also an ecology problem, an ethics problem, a medicine problem, a governance problem, and a memory problem. The conservative view is simple. With present technology, Proxima is not a practical human destination. A robotic interstellar flyby is more plausible than a crewed mission, especially if future technologies can accelerate very small probes to high speeds without requiring them to carry all their energy. But even that remains unsolved at the level of a completed mission. We do not yet have the full system: propulsion, targeting, shielding, onboard instruments, communication, power, and data return, all proven together across interstellar scale. The more radical view is that future civilization may develop methods that make the first interstellar probes possible within timescales people can emotionally grasp. That would not break physics. It would mean we had learned to use physics differently. Enormous laser arrays, advanced fusion systems, new materials, autonomous repair, and ultra-miniaturized instruments could shift the boundary. But each of those phrases hides its own mountain of work. So the uncertainty is not whether Proxima exists, or whether it is near by stellar standards. Those are secure. The uncertainty is whether technological civilization can turn secure knowledge into actual crossing. And what kind of crossing would count? A flyby? An orbiter? A lander in the system? A human crew? A self-sustaining migration? Each version is harder than the last. The word reach is not one thing, it has layers. To see Proxima through a telescope is one kind of reach. To send a signal, there is another. To send a tiny probe past it is another. To slow a spacecraft into orbit is another. To send humans and bring knowledge home through living memory is something else entirely. This is why the title must be handled carefully. Even the closest star is out of human reach now, but not because the universe has declared a permanent verdict. It is out of reach because our machines are still young, our energy is still limited, our lifetimes are short, and our best spacecraft are built for a solar system that, compared with the nearest star, is still only the beginning of the road. The future may move the boundary. But tonight, the boundary is here. Proxima Centauri matters because it is not alone in what it teaches. It is the first marker in a larger geography that humans are only beginning to feel correctly. The Sun is not isolated in the absolute sense. It is one star among many, moving through the Milky Way with a family of planets, dwarf planets, comets, dust, magnetic fields, and old debris. Around us, in every direction, other stars move through the galaxy too. Some are larger than the Sun, some are smaller, some are young and blue-white, some are old and quiet, some carry planets, some likely carry many. The galaxy is not empty between them, but it is sparse in a way the human mind is poorly built to accept. The nearest of those stars is Proxima. That makes it the beginning of our local stellar neighbourhood. But a neighbourhood of stars is not like a neighbourhood of houses. Houses are close because people can walk between them. They share roads, fences, sounds, weather, delivery routes, and accidents. Stars can be neighbours while being separated by distances so large that light itself takes years to cross. The Sun and Proxima are local only because the Milky Way is so much larger. Their nearness is real, but it belongs to the galaxy's scale, not ours. This is the larger system Proxima connects us to. The difference between a solar system and a stellar neighbourhood. A solar system is a realm bound tightly around one star. The planets orbit in years, decades, or centuries. Light crosses the main planetary region in hours. Gravity ties the architecture together. The Sun dominates motion, energy, climate, and time. Even the distant objects in the Kuiper belt and scattered disk are part of the Sun's extended story. They are cold and remote, but still shaped by our star. A stellar neighbourhood is looser. It is made of stars travelling through the galaxy on their own paths. They are not arranged like planets in neat rings around the Sun. Proxima does not orbit us. It is not the next member of our solar system. It belongs to another gravitational life, associated with Alpha Centauri A and B, while the whole system moves through the galaxy. The space between us is not an outer suburb of the Sun. It is the gap between star systems. That gap changes what home means. For almost all practical purposes, the solar system is the largest home humans have. Earth is the only world where our bodies are native, but the Sun's realm is the wider physical environment we can currently send machines through. It contains the Moon, Mars, the asteroids, Jupiter's moons, Saturn's rings, the ice giants, comets, and the heliosphere, the bubble shaped by the solar wind as it pushes into the surrounding interstellar medium. Voyager crossed beyond the main influence of that solar wind, giving us direct measurements from the boundary region, where the Sun's outflow gives way to the medium between stars. Even that boundary can sound like an exit. But it is not an exit in the sense people imagine. Leaving the heliosphere is not like leaving the solar system as a gravitational domain, and it is certainly not like arriving in another system. It is more like stepping beyond the weather of your own star, while still being nowhere near the next town. The Sun's gravity extends outward over immense distances. The Oort cloud, a theoretical reservoir of icy bodies, may reach thousands to perhaps tens of thousands of astronomical units from the Sun, depending on how its boundaries are defined. Even then, Proxima lies farther still. That thought is useful because it stops us from drawing the wrong border. The solar system does not end in one clean line. It fades through zones, planetary orbits, belts of small bodies, the solar wind's bubble, the distant realm of long-period comets, and finally the wider galactic environment. Proxima begins not just after the last planet, but beyond layers of decreasing familiarity. The road to the nearest star would pass not through a simple empty corridor, but through the gradual thinning of the Sun's immediate presence. And the Sun itself would change behind us. From Earth, the Sun is everything. Daylight, weather, climate, photosynthesis, seasons, warmth, and the basic rhythm of life. From the outer solar system, it becomes a bright star. From interstellar space, it becomes one light among others, though still the one that carries our origin. A spacecraft travelling toward Proxima would watch the Sun shrink into the kind of object we now see from Earth as distant points in the sky. The emotional reversal is exact. To go to another star is to make your own star look like one. That is a simple image, but it carries a great deal of science. Brightness falls with the square of distance. Move twice as far from a light source, and the light spreads over 4 times the area. Move 10 times farther, and the light is 100 times weaker. This inverse square law shapes radiation, visibility, solar power, and the fading of radio signals. It is why solar panels become less effective far from the Sun. It is why communication across deep space requires large antennas, sensitive receivers, and careful pointing. It is why interstellar missions cannot rely on the Sun in the way inner solar system missions can. The farther a spacecraft goes, the less Earth can bathe it in energy or attention. Near Earth, spacecraft can receive frequent tracking, strong solar power, and relatively manageable signal delays. In the outer solar system, sunlight is weaker and communication takes hours. Between stars, solar power becomes almost irrelevant unless the spacecraft carries extraordinary collecting area, and communication becomes a whisper spread across years. The physical environment has changed, but so has the relationship between machine and maker. Proxima also connects us to the larger question of planetary abundance. When astronomers began confirming exoplanets around other stars, the night sky changed again. Stars were no longer only suns in the abstract. Many were hosts. Planets turned out to be common. We now know that planetary systems are not rare decorations. They are a normal outcome of star formation in many environments. That makes the nearest star more emotionally charged. Proxima is not just a lamp in the dark. It is part of the evidence that nearby stars may have worlds, and that our solar system is one version of a broader galactic pattern. But common does not mean accessible. This is another illusion Proxima corrects. If planets are everywhere, it is tempting to imagine an abundant future of travel among them. In scientific terms, abundance is about existence. In engineering terms, access is about energy, time, and survival. The galaxy may be rich in worlds, while still being functionally enormous to bodies like ours. A treasure can be common and unreachable at the same time if the rooms are separated by oceans of light years. The larger system, then, is not just the Milky Way. It is the structure of our condition inside it. We live in a galaxy full of stars, probably full of planets, governed by laws we can learn with remarkable precision. We can measure nearby stars, we can infer planets, we can map motions, we can detect light that left before our current lives began. But our physical reach remains concentrated around one star. The solar system is already difficult. The nearest neighbouring system is another order of challenge. Proxima shows us the shape of the first boundary beyond home. Not a wall, not a warning sign, not an edge where physics becomes strange. Just the ordinary spacing of stars. And ordinary spacing in a galaxy is enough to humble every human idea of near. There is a kind of sadness hidden in Proxima Centauri, but it is not despair. It is the sadness of proportion. A child can learn its name, a telescope can locate it. A paper can describe its mass, its distance, its spectrum, its possible planets. A diagram can place it beside the Sun and Alpha Centauri. A simulation can show a spacecraft arcing outward, leaving the planets behind, turning the Sun into a brighter star among many. On a screen, the journey can be smooth. The camera can glide. The years can pass in seconds. Reality does not glide that way. Reality has mass. That is what makes the nearest star emotionally powerful. It sits close enough to enter human language, but far enough to resist human possession. We can put it into a sentence more easily than we can put a probe into its neighbourhood. We can say 4.25 light years before a candle flickers. But the actual crossing would require a civilization to gather energy, build hardware, preserve purpose, and accept delay on a scale that our daily lives almost never ask of us. Human beings are not naturally built for that kind of patience. Our bodies are short-lived. Even a long human life is counted in decades. Our attention moves by hunger, weather, work, grief, sleep, and the small urgencies of the day. Our politics often struggles to think beyond election cycles. Our technology renews so quickly that a machine from 50 years ago can feel ancient, even if it still works. And yet the stars ask questions in units that dwarf all of this. They do not care how fast a decade feels to us. The nearest star asks, can a brief creature make a long promise? That may be the true emotional centre of interstellar travel. Not conquest, not escape, not the loud dream of spreading everywhere. Something quieter, a willingness to build for a horizon no one alive may personally reach. A willingness to separate meaning from immediate reward. a willingness to let exploration become an inheritance rather than an achievement. This is not entirely foreign to us. Human beings have built cathedrals that took longer than one lifetime. We have planted trees whose shade was meant for descendants. We have preserved languages, seed banks, archives, graves, songs, and scientific records across generations. We know, in small ways, how to act beyond ourselves. But interstellar travel stretches that habit to an almost severe form. A mission to Proxima might require not just engineering patience, but cultural patience. The ability to care for a result that arrives after the original builders are gone. And still, the science remains practical. If a probe ever crossed to Proxima, it would need a purpose specific enough to justify the journey. It might measure the star's wind and magnetic environment from inside the system. It might image planets directly at close range, if its instruments and timing allowed. It might sample dust conditions between stars. It might observe Proxima b or other bodies in ways no telescope near Earth could match. It might test whether interstellar navigation, autonomy, and communication can work at all. The first interstellar mission would likely be as much about proving the path as studying the target. That is another emotional shift. We often imagine the destination as the prize, but for Proxima, the journey itself would be the experiment. Could a spacecraft survive acceleration? Could it maintain orientation? Could it protect itself from dust? Could its instruments function after decades? Could it recognize the target system autonomously? Could it transmit home? Each success would become a new kind of evidence, not only about Proxima, but about whether humanity has crossed a threshold in capability. The star would be both subject and witness. If a signal came back from a probe near Proxima, the first data might not be a beautiful image. It might be a confirmation tone, a position, a temperature, a particle count, a faint carrier wave rising from noise. To a casual listener, almost nothing. To scientists, engineers, and anyone who understands the distance, it would be one of the most astonishing sounds in history. Matter from Earth, having crossed the gulf between stars, still able to speak. There is no need to exaggerate that. The truth is already enough. A message from Proxima's neighbourhood would have travelled for more than 4 years after leaving the spacecraft. It would arrive not as a live event, but as delayed proof. The probe would have already moved on if it were a fast flyby. Its encounter would be past. Its images, if any, would be old before they were seen. And yet they would be new to us, because interstellar distance makes knowledge arrive like light from memory. This delay changes the emotional texture of discovery. On Earth, discovery often feels immediate. A door opens, a fossil appears. A microscope slide reveals a structure. A rover sends back an image from Mars after minutes of delay, and the mission team reacts while the machine is still present in a meaningful way. At Proxima, discovery would be more like receiving a letter from a place and time you cannot answer quickly. It would be intimate and unreachable at once. Perhaps that is why the closest star can feel almost dreamlike. Dreams are near to consciousness but hard to hold. They happen inside us and vanish when we try to grasp them. Proxima is not a dream. It is a real star with measurable properties. But emotionally, it occupies a similar border. It is near in knowledge, far in touch. Present in light, absent in reach. Specific enough to love as an object of curiosity, distant enough to remain unpossessed. That unpossessed quality may be healthy. A great deal of modern life trains us to think that knowledge should become control, and that attention should become access. We see something, map it, image it, describe it, and then expect the next step to be ownership or arrival. Proxima resists that habit. It reminds us that understanding is not the same as possession. A thing can be known and still beyond us. A place can be real and still not available. Science is not weakened by that humility. It is strengthened by it. Because the goal of science is not to make the universe smaller than it is. The goal is to let reality become clearer, even when clarity makes the universe feel larger. Proxima does exactly that. It takes the comforting word neighbour and fills it with 4 years of light travel, Trillions of kilometers, propulsion limits, radiation hazards, dust impacts, signal delays, and the fragile endurance of machines. It makes the universe more honest. And honesty has its own quiet beauty. The nearest star does not promise that we will arrive soon. It does not flatter human ambition by becoming easy. It does not close the future either. It simply stands at the first true distance beyond home and asks us to look carefully at what exploration costs when the scale is no longer human. Maybe that is enough for tonight. Not an answer that ends the dream, but one that changes its shape. A star can be close enough to guide our imagination and still far enough to teach restraint. The closest star to Earth is not close. By now, that sentence means more than it did at the beginning. At first, it was a contradiction, almost a trick of language. Closest should mean near. Neighbour should mean reachable. A star only 4¼ light years away should feel like the next place, the first step, the obvious beginning. Compared with the width of the Milky Way, Proxima really is nearby. Compared with galaxies, it is almost touching us. Compared with the observable universe, the distance is so small that astronomy can call it local without dishonesty. But the human meaning of close has been quietly dismantled. Close enough for light is not close enough for bodies. Close enough for measurement is not close enough for machines. Close enough for imagination is not close enough for arrival. Proxima has taken one familiar word and separated it into layers. Optical closeness, mathematical closeness, galactic closeness, engineering closeness, biological closeness. These are not the same thing. The title only works because we tend to collapse them. We say closest, and the mind reaches for a path. Science says closest and gives us a scale. That is the transformation. Proxima is not merely the first star on a list. It is the object that teaches us how to read the list correctly. Without it, nearby stars can sound almost domestic, like a neighborhood one might walk through if only the night lasted long enough. With Proxima placed honestly before us, the neighborhood becomes stranger. The first house is beyond every road we know how to build. The first porch light takes years to reach us. The first reply to a signal would come back after enough time for a child to grow into a different version of themselves. That is not poetic exaggeration. It is the ordinary consequence of 4.25 light years. The number now carries its mechanisms with it. It carries the speed of light, about 300,000 kilometers per second. It carries the scale of a light year, nearly 9.46 trillion kilometers. It carries the total distance, roughly 40 trillion kilometers. It carries the Voyager comparison, where 17 kilometers per second, a speed almost absurd by human standards, becomes too slow for interstellar hope on human timescales. It carries the 1% of light speed thought, where even an extraordinary 3,000 kilometers per second still leaves a voyage measured in centuries, if no further complications are included. And there are always further complications. To return to the hook honestly, we must bring everything back with it. Propulsion, braking, power, dust, radiation, signal delay, autonomy, and the aging of machines. The closest star is out of human reach not because one number is large, but because every part of a mission becomes difficult at once. Speed helps one problem and worsens another. A faster probe shortens cruise time, but makes dust impacts more dangerous and arrival more fleeting. More shielding protects instruments or bodies, but adds mass. More mass demands more energy. More energy demands larger systems. Larger systems create more failure points. A simple line drawn from the Sun to Proxima becomes, in engineering terms, a knot. This is why the phrase out of reach has to be handled with care. A star is not out of reach in the same way a fictional place is out of reach. Proxima is real. Its light reaches us. Its position is measured. Its small shifts against the background sky reveal distance. Its spectrum reveals a cool red dwarf. Its radial velocity behavior helps show the gravitational hints of orbiting worlds. Its flares have been observed. Its place in the Alpha Centauri system is part of the map of our local stellar environment. In knowledge, Proxima is already inside the human world. In travel, it is not. That distinction is now the heart of the story. We are not trapped in ignorance. We are limited in motion. We are a species whose instruments have outrun its vehicles. Our telescopes, detectors, and mathematics have made us larger in perception than we are in physical reach. The mind can stand near Proxima because light and thought are cheap compared with mass. But a spacecraft has to pay every cost that thought avoids. It is easy to underestimate how remarkable that imbalance is. For most of history, human knowledge was bounded closely by human movement. To know a valley, someone had to enter it. To map a coastline, ships had to sail near it. To understand a mountain pass, bodies had to cross it. Astronomy changed that relationship. It allowed humans to know places they could not visit. We learned the composition of stars before we could leave Earth. We measured galaxies before we touched the moon. We detected planets around other suns before any machine had crossed even a single light year. Proxima belongs to that revolution. It is remote knowledge at its most intimate. The nearest star is close enough to be scientifically detailed and far enough to remain physically inaccessible. It lets us feel the strange modern condition of astronomy. We can know without going. We can measure without touching. We can receive without arriving. And yet, because humans are embodied creatures, knowledge does not fully satisfy the old desire. There is still a difference between seeing the spectrum of a star and watching it rise from within its own system. There is a difference between inferring a planet through stellar wobble and seeing its crescent directly from a passing probe. There is a difference between saying a red dwarf flares and being able to measure its storm of particles from nearby space. Science can do astonishing things from a distance, but distance still withholds certain kinds of intimacy. This is where the opening contradiction returns changed. At first, the closest star is not close sounded like a warning against naive optimism. Now it sounds more like a precise description of our place in cosmic history. We have reached the stage where we can identify the first stellar neighbour clearly, but not the stage where we can visit it. We are not blind. We are not yet interstellar. We live in between. That in-between state may define us for a long time. It is possible that the first true interstellar craft will be small, not grand. A thin sail, a tiny probe, an almost weightless instrument package accelerated by a beam. It may not carry people. It may not slow down. It may not send back images as rich as imagination wants. It may give us a handful of measurements, fragile and delayed, from a few hours near a red star. And even that would be one of the greatest crossings ever attempted. Or perhaps the boundary will remain for centuries. Perhaps the solar system itself will occupy us for a long future. The Moon, Mars, asteroids, icy moons, orbital habitats, telescopes far from Earth, and machines that learn to live around one star. That would not make human exploration small. It would only make the first star beyond the Sun more honest as a limit. The Hook asked why even the closest star is out of human reach. The deeper answer is this: because reach is not seeing, not naming, not calculating, not hoping. Reach means moving matter across the gulf and still having it arrive with purpose. Reach means carrying energy, memory, protection, instruments, and intention through years of darkness. Reach means building something that can survive the difference between a star as light and a star as place. Proxima Centauri is the nearest star. And that is exactly why it matters that we cannot yet go there. It is the closest test of the farthest dream. If Proxima Centauri were farther away, the lesson might feel easier to dismiss. We could say, of course it is unreachable. Of course a distant star defeats the machinery of one young civilization. Of course the galaxy is too large to cross casually. But Proxima does not let us use that comfort. It is not a remote star chosen for drama. It is not on the far side of the Milky Way. It is not buried in a nebula or hidden behind dust in the galactic center. It is the nearest known star beyond the Sun. And still, it is enough. Enough distance to turn light into a 4-year messenger, enough distance to turn radio communication into an exchange measured across childhoods. Enough distance to make Voyager's enormous speed feel almost still. Enough distance to make propulsion, braking, shielding, power, navigation, autonomy, and data return all become central at the same time. The first star is not a gentle step into a larger world. It is the first clean demonstration that the galaxy is built on a scale where seeing and going have parted company. That is the synthesis of the whole story. Proxima is near in evidence, far in engineering. The evidence is strong because astronomy has learned how to let light speak. Parallax gives the distance by using Earth's orbit as a measuring baseline. Spectra reveal the star's cool red dwarf nature by spreading its light into a pattern of wavelengths and lines. Changes in position and motion place it within the Alpha Centauri system and within our local stellar neighbourhood. Radial velocity measurements can reveal the subtle tug of orbiting planets by watching the star move in response. Photometry can catch changes in brightness, including flares. Models then help scientists interpret what these signals may mean for the star, its planets, and their environment. None of that requires a rival. That is both the triumph and the ache. A photon can cross 4.25 light-years without a launch vehicle. It does not need food, shielding, navigation, spare parts, or a mission budget. It leaves the star and, years later, may land in a detector on or near Earth. It carries information because light interacts with matter in precise ways. It can be stretched by motion, absorbed by atoms, brightened by flares, dimmed by transits, and measured by instruments built to notice changes too small for the human senses. Through light, the universe becomes legible across distances our bodies cannot cross. A spacecraft is different. A spacecraft must be built inside the physical economy of mass. It must be accelerated. If it wants to arrive slowly, it must decelerate. If it wants to protect itself, it must carry shielding. If it wants to think, it must carry computers. If it wants to see, it must carry instruments. If it wants to speak, it must carry a transmitter and aim its signal across the dark. If it wants to live as a machine for decades, it must manage power, heat, radiation, memory, and failure. This is why the same distance can be scientifically intimate and physically severe. A telescope can gather Proxima's light tonight, but a probe cannot casually follow that light back. At every step, matter pays. It pays in energy, it pays in time, it pays in wear, it pays in risk. A mission designer cannot say nearest and receive a discount from physics. The universe does not charge by emotional importance. It charges by velocity, mass, distance, and the laws that connect them. The numbers form the skeleton of the truth. About 4.25 light-years, about 40 trillion kilometers, about 268,000 astronomical units. Light takes years. A radio round trip takes more than 8 years. A Voyager speed crossing would occupy tens of thousands of years. 1% of light speed still means centuries. 10% of light speed starts to sound human, but demands extreme energy and creates violent encounter speeds with dust and gas. Every attempt to shorten time increases some other burden. But the numbers alone are not the story. The mechanisms give the numbers weight. Momentum explains why rockets must throw mass backward. The rocket equation explains why carrying propellant becomes punishing as desired speed rises. Kinetic energy explains why faster motion grows expensive faster than intuition expects. The inverse square law explains why sunlight and signals weaken with distance. Stellar activity explains why a close-orbit planet around a red dwarf may face flares and radiation, even if it lies in an interesting temperature zone. Communication delay explains why an interstellar probe must be autonomous. Reliability explains why the mission is not finished at launch, or even at cruise, but only when useful data returns. The uncertainties give the story honesty. It is known that Proxima is the closest known star to the Sun. It is known that it is a red dwarf, faint to the naked eye and much smaller than the Sun. It is strongly supported that at least one planet, Proxima b orbits close to it. It is inferred through models that any planet in that environment would face complex conditions shaped by stellar activity, possible tidal effects, atmosphere, and radiation. It is speculative whether future laser sails, fusion craft, or other advanced systems could send probes there on timescales that feel human. It is far more speculative to imagine crewed travel, orbital arrival, or settlement. This separation matters because wonder without boundaries becomes misinformation. Proxima does not need us to pretend. We do not need to say it is impossible forever. We do not need to say a habitable zone planet is a second Earth. We do not need to say starflight is around the corner. We do not need to say the dream is dead. The true situation is more interesting. The nearest star is real, measured, physically rich, and beyond practical human travel for now. It is not unreachable because of ignorance. It is unreachable because knowledge has moved faster than our machines. That may be the most human part of the story. We often learn the shape of a desire before we learn how to satisfy it. We named the moon before we landed there. We mapped Mars before we drove across its soil. We knew the stars were suns before we sent any machine beyond the planets. Science repeatedly gives imagination a sharper target. It turns longing from a blur into a coordinate. Proxima is one of those coordinates. A faint red dwarf in the direction of Centaurus, the nearest known star, a member of the Alpha Centauri system, a place whose light is already old when it reaches us, a star close enough for measurement and too far for ordinary ambition. It stands at the edge of the solar system's psychological boundary, not because it marks where the sun's gravity ends, but because it marks where our present sense of exploration changes form. The final synthesis is quiet. We are not a star-faring species yet. We are a star-measuring species, a star-watching species, a species that has sent machines beyond the planets and learned that even the nearest sun beyond our own remains separated from us by the full seriousness of physics. That is not failure. It is the first honest map. And a good map does not shrink the world. It tells you where you truly are. So let the last image be small. Not a roaring rocket, not a shining fleet, not a doorway opening between stars. Just the sun, seen from very far away, reduced to a point of light among other points. The same sun that warms oceans, turns leaves toward morning, raises storms, pulls planets, and holds the long memory of Earth in its gravity, now appearing almost like any other star to a machine travelling outward. That is what the road to Proxima would do first. Before it brought us closer to another sun, it would make our own sun distant. There is something quiet in that reversal. From Earth, the sun is not an object among objects. It is the condition of almost everything we know. It is weather, colour, harvest, shadow, skin, season, and time. It is so close to our lives that we often forget it is a star at all. But on the way to Proxima, the sun would slowly become what Proxima is to us now, a measured light, a remembered origin, a bright point that means home only because something alive or built once came from there. Maybe that is why the nearest star feels so difficult to think about clearly. It asks us to imagine leaving not just a planet, but a scale of life. Earthly distance is full of return. You can walk away from a house and still come back before dark. You can cross an ocean and call home. You can fly over continents and arrive tired, but still within the same day's ordinary world. Even the moon, impossibly far by older human standards, remained close enough for voices to cross the gap in seconds. The astronauts could look back and see Earth whole, bright, and near enough to return from. Proxima does not offer that kind of nearness. It does not answer quickly. It does not wait just beyond the horizon. It does not become approachable because it is first on the list. Its light has already made the journey, but that is the privilege of light. Matter must take the long way. Machines must endure. Bodies must be protected. Signals must crawl home at the fastest speed the universe allows, and still take years. So the title leaves us with a corrected kind of wonder. Not the easy wonder that says the stars are waiting for us. A harder, calmer wonder. The stars are real, and the nearest one is already almost beyond the frame of human action. That does not make Proxima cold in meaning. It may make it more meaningful. A reachable thing can become ordinary once reached. A distant thing remains a teacher. Proxima teaches the difference between a name and a journey, between a map and a crossing, between seeing and arriving. It teaches that the universe is not scaled to our impatience. It teaches that our tools have extended our sight farther than our hands, and that this imbalance is not shameful. It is where we are. For now, humanity lives in the age of first knowledge. We know the nearest star is there. We know its light takes years to reach us. We know it is small, red, faint, and physically different from the sun. We know planets can exist around such stars. We know that even a real neighbouring system remains separated from us by energy costs, mission lifetimes, communication delays, and the fragility of machines. We know enough to stop pretending that near is a simple word. And we know enough to keep looking. That matters. Because looking is not passive when it is done with care. To measure parallax is to turn Earth's orbit into an instrument. To read a spectrum is to let atoms identify themselves across years of darkness. To detect the tug of a planet is to notice a star's almost imperceptible dance. To listen for faint signals from distant machines is to practice a kind of patience that belongs to science at its best. Perhaps one day a probe will leave the solar system with Proxima as its true target. It may be smaller than our old dreams. It may not carry a crew, a cabin, a garden, or a flag. It may be a fragile piece of intelligence wrapped in shielding, or a tiny sail pushed by light, or something built with technologies that are still only sketches in our present imagination. It may fly through the Proxima system too quickly to linger. It may send back only a thin stream of data. The people who receive it may not be the people who launched it. Still, if that signal comes, it will mean something enormous. It will mean that matter from Earth crossed the space between stars and spoke after arrival. But that is not tonight's world. Tonight, Proxima remains what it has been throughout this journey. The first neighbour that cannot yet be visited, the nearest star that teaches distance, the small red point whose closeness is true only when spoken in the language of galaxies. It is not cruel. It is not inviting us with false promises. It is simply there, doing what stars do, burning, flaring, moving, holding its planets if they are there, sending its light outward in all directions. Some of that light comes here. It enters telescopes. It becomes measurement. It becomes a number on a page, a curve in a graph, a line in a catalogue, a thought in a human mind late at night. It becomes the feeling that the universe is both knowable and unreachable, generous and severe, open to understanding, but not easily crossed. And maybe that feeling is the right place to leave it. Not with the fantasy that the first star is waiting just beyond our current courage. Not with the despair that we will never go. But with the quieter truth that the universe has given us a first step so large that learning its size is itself an achievement. Proxima Centauri is the closest known star beyond the Sun. Its light is already here. Its place is already measured. Its distance is already telling us the truth. And for now, that truth is enough to humble the dream without extinguishing it. So if you are lying still, somewhere on Earth, beneath the same sky that hides Proxima from unaided eyes, you can let the scale rest without trying to solve it. The nearest star is not close, but it is near enough to remind us that our home is part of a larger dark, and far enough to remind us that not every light in the sky is a place we are ready to touch. Sight is not a rival. A name is not a crossing. And the first star beyond the Sun remains where it has always been, close in the universe, distant from the hand, shining softly across 4 years of darkness.